In this video, we're going to talk about summing a geometric series. So a geometric series is a sum of a geometric sequence. And so we're going to end up having the following formulas. So if we sum a sub k from k equals 1 to n, that's s sub n in general. For a geometric sequence, a sub k can be written as a sub 0 times b to the k. Or if you want to think of this instead in terms of the first term, it's a sub 1 times b to the k minus 1. And we're summing that up from k equals 1 to n. We can also change the index here if we want to call it j. J is just a k minus 1. So we can sum from j equals 0 to n minus 1, a sub 1 times b to the j. So three different ways of writing that. But here's what the formula we end up with. We end up with the formula a1 times the fraction, where the numerator is 1 minus b to the n power, and the denominator is 1 minus b. Or you can multiply top and bottom of this fraction by negative 1 and rewrite it as b to the n minus 1 over b minus 1. The second version here is probably better when b is bigger than 1, and the first version is better when you've got a b that's between 0 and 1 so that you get positives everywhere. But either way, those are the same formula. Now, let's actually see if we can prove that formula. Okay, so I take a sequence, first of all, that's geometric, but starting with the term 1. 1, the second term would be b, next would be b squared, b cubed. I'm just multiplying by b each time, and you end up with b to the n minus 2 and b to the n minus 1. Since I'm starting with 0 b's at the first one and ending with n minus 1 b's multiplied together on the last one, this is actually n terms. Okay, I'm going to multiply that by 1 minus b. So I just use the distributive property or long multiplication here, the basic multiplication algorithm. I'm going to multiply each term by negative b. Well, first of all, being negative at the bottom and positive at the top makes all the terms negative. Secondly, all the powers are going to go up 1. So this b to the n minus 1 becomes a b to the n. And the one before that, instead of n minus 2 for the power, now becomes n minus 1. And the first one is b, and then b squared and b cubed. But they're all negatives. Now multiplied by 1, it just stays the same, and I've lined them up, lining up like terms. Now if you notice, all of these terms in the middle have a negative one up here and a positive one here. They just cancel out and disappear. And so what's left is only the first term, 1, and the last one is negative b to the n power. So it's kind of like you got a long telescope, and you just collapse the whole thing. And the only thing that's left are the two n's, 1 and minus b to the n. So what do we see is that if we take this 1 times this, we get this one here at the end. So this is it right here. Parentheses 1 plus b squared plus b cubed up to b to the n minus 1, close parentheses, times open parentheses 1 minus b close parentheses equals 1 minus b to the n power. Now I'm going to divide both sides by 1 minus b, and I get this here. So this is the sum of a n-term geometric series where the first term is 1. Well, what about a more general one? Well, if I multiply both sides by, say, some number a sub 1, and then I distribute on the left, we see that the one on the left is a1, and the second term is a1 times b, and the next one is multiplied by another b, a1 times b squared, and so forth. So this left side is exactly the sum from k equals 1 to n of a1 times b to the k minus 1, which is exactly a geometric series, the first n terms of a geometric series. And what do you get? You get a1 times 1 minus b to the n over 1 minus b. So we just proved that formula. So we derived and proved this formula. Here it is again in a little box. Should be memorized, probably. And this formula, a1, of course, as usually stands for the first term. B is called the common ratio. Some people use an R there. I prefer to use a B for base. And n is the number of terms that we're adding together. So here are a couple of problems for you. Sum the first 20 terms of a geometric series with initial term 5 and common ratio 2. And for part B, compute the sum k equals 1 to 50 of 6 over 3 to the n. When you've got answers, come back and check them with the video. Press pause now. Hopefully you're working these out yourself. So these are pretty straightforward once you just identify everything. So this one says it's geometric series, so we're going to use the formula that we just came up with. There are 20 terms, so that's n. The initial term is 5, that's A1. The common ratio is 2, that's their base, that's B. And I prefer for when the base is bigger than 1 to use this version of the formula where I multiply top and bottom of the fraction by -1. So plugging in there, A1 is 5, B is 2. 2 minus 1 is 1 on the bottom, so it's just 5 times 2 to the 20th minus 1. 2 to the 20th is 1,048,576. Subtract 1, that's 1,048,575. Multiply by 5, that's 5,242,875. Yeah, I used a calculator to help me with some of that. Okay, the next part, it's also a geometric sequence. We've got a first term by plugging in k as 1. That should not be both n and k. Either both n's or both k's. That's there. It should be there. I'm going to change it to k here. Okay. And I need to do the same here. Okay. Continuing on. The first term, you just plug in k is 1. K is 1 gives you 3 on the denominator, 6 on the top. 6 divided by 3 is 2. So the first term is 2. Then the base is just 1/3. Every time we increase k by 1, we're multiplying by another 1/3. And n is 50. You can always find n be the top number minus the bottom number plus 1. Okay, so if you start at 1, it'll just be the top number. All right, so that's that. So pretty simple. Just plug in the formula. The first term is 2. 1 minus the base of 1/3 to the 50th power over 1 minus the base. 1 minus 1/3 is 2/3. And then this is 1 over 3 to the 50th. If I get a common denominator in the numerator, just look at the top and get a common denominator there, 3 to the 50th. 1 is 3 to the 50th over 3 to the 50th. Now let's see what I can do here. The 2 divided by that 2 is going to cancel completely. That 3 is going to flip up and multiply, canceling that down to 3 to the 49th. So we're going to end up with 3 to the 50th minus 1 over 3 to the 49th. Now at this point, you got a lot of by hand arithmetic or some calculator arithmetic, but even like a TI-84 is not going to work. But luckily I have a TI Inspire, and it was able to do 3 to the 50th minus 1 is this ungodly big number here. And 3 to the 49th is this denominator here. I'll let you read that yourself. I'm not going to read it out loud. And when you divide these two, basically you get 3. It's 3 to, it's actually just a little less than 3, but it's 3 to lots and lots and lots of decimal places. I'm not even sure how many. So basically the answer is pretty much 3. All right, here's another problem, sort of a real world type problem. Legend has it that when the inventor of the game of chess presented to the king was so grateful for this awesome game that he asked what gift he could give. And the inventor said, well, my needs are quite simple. Give me 1 grain of rice for the first square, 2 grains of rice for the second square, 4 grains of rice for the third square, and so on, doubling the amount of rice for each square. So how much rice was he asking for? See if you can figure that out yourself. Press pause now. Well, a chessboard is an 8 by 8, 8 rows and 8 columns of little squares, and we're just talking about the little squares, for a total of 64 little squares. So the amount of rice is the sum of a geometric series, with A1 is 1, B is 2, and N is equals 64. So it's 1 plus 2 plus 4 plus 6 plus 8, and so forth. No, 6. 1 plus 2 plus 4 plus 8 plus 16 plus 32, and so forth. All right, well, the first term is 1, so that goes out here. There are 64 terms, so that's 2 to the 64th, then minus 1, over the base of 2 minus 1. 2 minus 1 is 1, so it's just 2 to the 64th minus 1. Again, I had my fancy calculator work this out. Let me see. This is let's see, thousands, millions, billions, trillions, quadrillions, quintillions. It's 8 quintillion 446 quadrillion and so forth. 744 trillion 73,709,551,615, or about 1.845 times 10 to the 19th grains of rice. Not bad. Well, this is more rice than the United States produces in over a decade. So really, he was asking for more than the worth of the entire kingdom's treasury. Crazy how fast that grows, huh? That's exponential growth for you, or geometric growth. All right. We're going to learn how to use some technology in the next video.